Hello, in this clip of our astronomy lectures, we're going to cover astronomical measurements. We're going to continue with our series on astronomical measurements so that we can wrap our minds around the numbers and the units and the distances involved to scale the cosmos and put some of these celestial objects into perspective. So what we have to look at here is distance and try to understand how distant some of these celestial objects are. So on an everyday scale, we're used to using distances in kilometers, but when we start looking at further out objects like the stars in the night sky, we want to start thinking about light years away, and we want to contemplate, well, that star has given light off a long time ago, and we're seeing the history of that star in the night sky. So we're going to start equating time and distance together to make measurements. So it's very mind-boggling. The size and scale of the cosmos is extremely daunting. It's a very, very huge amount of space we're working with. So it's important to put into perspective the neighborhood objects in our solar system and then go beyond that. So let's first take a look at some of the units that we're used to. We're used to kilometers. So when we were talking about making a round trip, traveling from city to city, maybe you're traveling all around the Earth's equator, which is above 6,000 kilometers, we're going to use the kilometer unit to do that. And we know how to easily convert from kilometers to miles. So we also use it for near objects when we're looking out in the sky. Kilometers we can use for the moon distance, the average moon distance. The average moon distance, what do we have for the average moon distance? It's about 3.83 times 10 to the 5 kilometers. Okay. And what you have to note, there are times where the moon is closer to the Earth and times it's further away. This is explained by Kepler's laws. So here's the Earth, and then we got the moon orbiting around, and sometimes it's closer in distance. And that's called perigee, and sometimes the moon is further away. So I'll write moon here, and here's the Earth. There's the moon. So this is the moon when it's closest. So this distance will be less than this quoted average distance. And sometimes the moon is further away because it goes around the Earth in elliptical orbits. Again, explained by Kepler's law. And this would be apogee and perigee. So we'll also look at some other similar concepts with the planets going around the sun. Okay, so we can use this for the moon distance. Some other numbers that come into play are the distance to the ISS, the International Space Station. That's approximately 400 kilometers, okay, above the Earth. Okay, that gives you a good scale. Sometimes nearby asteroids, hopefully not too close, etc. We'll use the kilometer distance. Even sometimes with the sun, you'll hear the sun is this huge amount of miles away, so that comes into play as well. But what starts to become useful when we're looking at solar system distances is the astronomical unit, the AU. Okay? This is used for, SS stands for the solar system objects. Most importantly, the distances to all the different planets. Okay? So solar system objects are the neighborhood of our solar system. Our solar system neighborhood. Then, when we go outside our solar system, we start looking at these vast distances that are measured in this unit called the light year. So stars, galaxies, and the size of the cosmos, the observable universe, so to speak. the largest observable size we can see of our universe is about 93 billion light years across, and that's a lot of space. So we use light years when we start getting outside the solar system. And then the parsec is even a bigger unit of measure than the light year, but it's based on the Earth and dividing up the sky into coordinate degrees. So the parsec is for, again, large distances. There's not much of a difference between these two units, and I'll give you that conversion factor. So it's really important to know that. Now, typically, when you see a representation of, a planetary system on a poster, those are typically not to scale, because we'll see that the further out you go, the harder it is to represent those very large distances. Okay, so let's start with, we've already looked at the kilometer. So let's look at this astronomical unit. What is an astronomical unit, which we use the symbol AU for? Okay. An astronomical unit is defined as, if we take this model right here, the average Earth-Sun distance, okay? So this is a distance, it's a measure of the average Earth Sun distance. And you'll see that you get a whole table that lists the AU of all the planets, not just the Earth-Sun, but based on that standard measure or average Earth-Sun distance. So this, we could say 1 AU is equivalent to, and we have a nice equivalent in terms of meters and kilometers, is 1.50 times 10 to the 11 meters, okay? That's how many meter sticks it would take to make up an AU. That's a lot. And this is equivalent to 1.50 times 10 to the 8 kilometers. Okay, very, very large distance. Okay, so that would be the measure. Now, what you have to recognize again is that the Earth does not move around the sun in a circle. It moves around elliptical orbits, as do all the planets. So this is Kepler's laws. Kepler's first law says the planets move around the sun in elliptical motion. So what we'll have is times where the Earth and other planets are closer to the sun, and other times where they're further apart. So this number right here, 1 AU, will represent this average orbiting distance. So I put the sun at a focal point. So an ellipse has two focal points, two foci, and the Earth makes its yearly journey around the sun, its revolution or orbit. That takes 365.25 days. Sometimes the Earth will be further away, okay, like in the summer, and sometimes close to summertime. And sometimes the Earth will be, and I'll just say E for Earth, closer. This closer distance is called your perihelion. And aphelion is your further away distance. And all the planets do this too. So they all have average distances, but you have to know that sometimes those orbits are closer to the sun, sometimes further away. So this number is based on the average. Okay. So AU distances. Let's take a look at some of our neighborhood values here. Okay. So what do we have here? We have the Earth-Sun distance, which is this. Okay. So some examples. Not really used for the moon, because the moon's a lot closer, but you could put them in fractions. We have let's say Mars is approximately 1.5 AU. Now that's with respect to the sun, so you have to remember that we're going outward. So the inner planets like Mercury, Venus, they'll be less than 1 AU. And then we go to the outer planets like Mars, it's about 1.5 AU with respect to the sun. That would be the average Sun-Mars distance. And then we could look at some other ones, like we go through the asteroid belt and then we fly to Jupiter, and that's about 5.2 AU, okay, with respect to the sun. And we get out further and further, and we could go to some other values. I have a nice table here. We could go to Saturn, that's about 9.5 AU. I'll say 9.6 AU. And then you could go far, far out. If we look at things like Neptune, Neptune could be about 30 AU, just a little over 30 AU out there, and that's the furthest planet from the sun. And then beyond that, you can get to the dwarf planets, etc. And you could see that that gets to be daunting to scale up and put on a poster size, a good representation. Now, another good number for you, our furthest spacecraft, both spacecrafts, Voyager 1 and 2, are the furthest spacecraft from the sun, furthest spacecraft from Earth ever, I should say. And right now, I have to keep updating my numbers here. What we have for Voyager, okay. Voyager is approximately 152 AU, Voyager 1. That's really far, and Voyager 1 is on the edge of the solar system. It's leaving the influence of the sun. So that's a huge distance. And then we start getting into the really frosty parts of the Oort cloud and then exiting the solar system. Then we get into other units. So AU measures are huge. And if you're trying to do a representation of that, it's really can be very daunting. And typically there's a few exercises you could do on a scale like this. Now, if I were to go ahead and say, let me take 10 centimeters, so if I take a meter stick like this and 10 centimeters to represent 1 AU, okay, I'd say here's the sun, here's the earth. And then inside that realm, I might mark the distances of like, what do I have? I have 0.383 for Mercury, 0.723 for Venus, okay, and those are marked right here. Okay, and there's the Earth, and then I would make a mark for 1.5 for Mars AU. And then, like I said, if I represent every 10 centimeters on my string with an AU, I could go down the line, and then I get to about 5.2 for Jupiter, and then about 9.58 for Saturn, and then I move on, and the next one is Uranus, and it gets harder and harder to represent this, and Uranus is 19.2. So this is a double meter stick. So I'm going to get all the way to 19.2. And that is right around here. That becomes really hard to measure. 19.2, and then I go on to 30, and then let me go the whole distance to Voyager. So I would need 15 meter sticks at least to represent that distance. So trying to scale that cosmos can be very daunting, but that's one way you could do it. It's always fun to try to get some representation of those numbers. Now let's move on up and go to our next measure. All right, so we could do our AU measurements in the neighborhood. We use that conversion factor and give you some examples and get to the end. But the next one is a very important one for astronomy, and that is the light year. what is a light year? We have Ly. Sometimes I go Ly, so just a little warning. And a light year, you could think of this as like a light stick that measures distance. It's a measure of distance. Okay, it's a measure of distance based on the speed of light. And specifically, it is the distance It is the distance covered by light traveling at the speed of light in a vacuum, okay, 3 times 10 to the 8 meters per second. So as light moves that fast, it will cover a certain amount of distance. And if you let it travel for a whole year and you measure the distance it covered, that would be a light year. Okay, so it's really hard to imagine, but if you could think of this as a light stick, right? You let the light go and it's traveling at 3 times 10 to the 8 meters per second, which is 300,000,000,000,000 meters every second. And you do that, add up all the seconds. So every second you go 3 times 10 to the 8 meters, another 3 times 10 to the 8 meters the second after that, another 3 times 10 to the 8 meters the second after that. You add all those increments up so that all your seconds add up to the number of seconds in a year, and then you get your distance in meters, and that is a light year. It is a huge number, okay? So what we get when we do that value is we get 1 light year is equivalent to 9.46 times 10 to the 15 meters. Okay? And a lot of times if you want to do the kilometer conversions, 9.46 times 10 to the 12 kilometers, because it's 3 units difference between kilometers and meters. That's what a light year is. So you could convert values of light years into meters. So, and you'll see the utility is 1 light year covers a lot of meters, so it's a lot easier to work with these numbers than it is these huge numbers in scientific notation. Okay, so this is huge, and the way you derive this value is you use the speed of light and you use the time, and you could find out that distance in meters. So some examples of measures in light years would be the nearest star, Proxima Centauri, is 4.2 light years away, approximately. Okay. We could even say that the outer edges of the Oort cloud is estimated. Nobody knows this for sure. It's still new science. The Oort cloud boundaries, and I'll put a question mark there because we're always updating these numbers, is anywhere from 1 to 3 light years away. And then we could get into some other mind-boggling numbers here. Sirius, our dog star, the brightest star in the night sky, and I know I wrote this down, is about 8.2 light years away. Polaris, You know, we're looking at over 400 light years away, our North Star. And then if you look at the diameter of our galaxy, the Milky Way galaxy is estimated to be about 100,000 light years across. And then what else do we have there? We go beyond that to the nearest really big galaxy. There's a lot of other smaller galaxies that we've discovered recently, but the Andromeda galaxy is one you could see without aid. One of the furthest, it is the furthest object you should be able to see without any aid in the night sky. It's about 2.5 million light years away. And then beyond that, and then we go into the other neighborhood of galaxies, and we're talking about millions and billions of light years. And we know what we can observe, the observable universe, the diameter of that is 93 billion light years across. We get to some really large scale measures. So let me just show you how to derive this. It's really hard to memorize numbers, but I know we live in a day where we can look these values up and free up our brain space for other important tasks. But let me enlighten you to a light year derivation. Okay, so we could use that light year meter conversion to do most light year to meter conversions, light year to kilometer conversions. However, if perchance you don't have that conversion on you, you can always derive it. And the idea is to use the relationship distance equals rate times time to figure out what the meter equivalent to a light year is. And so what we could use is for a rate, we know the light year is based on the speed of light, c, 3 times 10 to the 8 meters every second in a vacuum. And 1 year is broken up into 31,536,000 seconds. So this is how it goes. So we take, if we want distance in meters, we take the speed of light as our rate times the time for a year. So we'd say, okay, light travels at 3 times 10 to the 8 meters every second. Okay, so I'm going to put over seconds here, which is equivalently another way of saying it. And I'm going to multiply by my time in years. So this is my rate, this is my distance, 1 light year, and then times time. Now, time in 1 year, let's start with seconds. I know there are 60 seconds in 1 minute. MIN is my short for minute. It's used by a lot of different people. And I know there's 60 minutes in 1 hour. And I know there's approximately 24 hours in a day. As we discussed earlier, that's not exact. Okay. And then there are how many days in a year? Well, I'm going to include leap years and say 365.25 days in 1 year. And I multiply by that entire conversion factor, and I cancel out my seconds, cancel out my minutes, cancel out my hours, cancel out my days, and I get how many meters are in a light year. And this will give me my answer in meters for a light year. Okay, that's how we do it. Now, on to our last measure, the parsec. Parsec, excuse me. Parsec is a larger measure than a light year, and it's based on how we divide the sky up. So when we look up at the sky, we divide that sphere that surrounds us into 360 degrees. And each degree is further divided up into 60 minutes. And each minute is further divided up into something called seconds, and we call it arc seconds. And it's a typical measure we use for stars and parallax, which is another topic we'll cover in our series. Okay, so a parsec, the way we're going to define a parsec is based on the Earth's divided up sky. So we could say it's the mean radius Okay, so we could say it's the mean radius of Earth's, we could say a parsec is the mean radius of Earth's orbit as it subtends an angle of 1 arc second. Okay, it's also the distance to an object where the parallax angle is 1 arc seconds. So another way of thinking about that is the distance where the stellar parallax equals 1 arc second, which is another way of saying 1 with 2 dashes on there, 1 arc second. Okay, so anything that has that stellar parallax will give you a distance in parsec. So that would be 1 parsec in that case. Okay, and the angular measures, as stated earlier, are when you take the Earth in the center and you divide up the sky into 360 degrees. Okay, and then you take a little slice there of 1 degree, which equals 60 minutes, and that equals another 60 seconds, so that's 3,600 seconds. Okay, so we also call that arc seconds. You take one of those degrees, divide it into 60 pieces, and then take those arc minutes, divide them up into 60 more pieces, and you get an arc second. So anything that shifts that 1 arc second in the sky is equal to 1 parsec. So how do we do a parsec conversion? Well, we use this number right here, and we just use that as a conversion factor. That's all you need to know about now. Let's do some examples. Our conversions are fairly easy. So for AU, let's say an object, maybe an asteroid, is let's say we have an object, perhaps an asteroid, between the orbit of Mars and Jupiter. We see that it's 4.5 AU away, and we want to know the number of kilometers. Well, what we do is we take our unit that we know, 4.5 AU, times 1 AU, which is equivalent to, again, 1.5 times 10 to the 8 kilometers. And our AU cancel. And we get an answer in kilometers, which is, let's see, 4.5 times 1.5 times 10 to the 8th meters gives us 6.75 times 10 to the 8 kilometers. Okay. Now, if we do a simple light year conversion, let's say a star is approximately, let's say 12 light years away. So we have this star that is 12 light years away. How many kilometers away is it? Well, we could use our light year conversion. We could say 12 light years times my light year to meter conversion. And my light year to meter conversion, we have 9.46 times 10 to the 12 kilometers. I'm going to say kilometers in this case. Okay. I want to know how many kilometers away it is. And that's for every light year. That gives me a value that gets rid of the light years in kilometers. And that would be 1.14 times 10 to the 12, no, not 12, 14 kilometers. Okay, we're gonna, this is almost 10, so you're about to hop over to the next exponent here, and then you're multiplying by another factor of 10. So this makes sense. Always check that they do make sense. Okay, and that's how we do a typical light year conversion. And we could do the same thing for the star. We could convert this to parsecs. Let's say the star that we know is 12 light years away. How many parsecs away is it? Well, in this case, we just use our conversion. We know that we have 12 light years, and we're going to multiply by our light year parsec conversion. So we get rid of our light year, and we introduce our parsec, where 1 parsec is 3.26 light years. So it's pretty much like dividing 12 by 3.26, and we expect a smaller measure because a parsec is a larger measurement. And we get about 3.68 PC. Okay, and next question, next thought is, if you're given these distances in light years, can you figure out how long ago that light left that star or that object that we're looking at? And that's equivalent to something called look-back time. So if we have a star that is 12 light years away, what does that mean in terms of the light we're seeing? So okay, so if a star is 12 light years away, how long ago did that light leave the surface? Well, that would be 12 years ago. Okay, assuming a nice natural path, right? And traveling at the speed of light. So that light hasn't been manipulated anyway. So the idea is, if a star is 12 light years away, we're looking at its light from 12 years ago. We don't know what it's currently doing. We only know what that light was doing 12 years ago. So it's a mind-boggling concept. So when you look at stars, you're looking at the history of the light. So some of these stars are hundreds of light years away. If we look at the nearest galaxy, I shouldn't say the nearest galaxy, the nearest naked eye galaxy we could see with our own eyes, large galaxy, which is the Andromeda galaxy, that's about 2.5 million light years away. So we are looking at that galaxy's light from 2.5 million years ago. So we don't know what the light is currently now. We don't know what it looks like currently now. We have good models to predict what it's currently doing, but we're seeing that light from that long ago. And the further distance you are looking at further back in time. So some of these Hubble images that are looking at these galaxies far, far away, like 10 billion years, 10 billion light years away. We're looking at that light from 10 billion years ago emitted by those galaxies. So it's something called look back time, and it's really interesting to see the connection between distance, light, and time in these measurements. Okay, one last measurement thought. One of these other exercises you want to practice and think about is that when we're looking at how light is traveling through space and time and how long it takes for signals and light to reach different objects in the solar system and further beyond in our galaxy and beyond that. So if we have a lot of space probes out there. So for instance, if we had a space probe orbiting around Jupiter and we wanted to know how long that radio signal from that spacecraft could reach us here on Earth to decipher its coded photographs or other measurements it's been making for us, we like to be able to use and understand how to figure out how long it would take to reach us. Okay, so here's a problem, like how long would it take How long would it take a radio signal coming from the spacecraft orbiting Jupiter at about 5.2 AU away here on Earth? So 5.2 AU is with respect to the sun in this case. So first, what we want to do is our distance is 5.2 AU minus 1 AU, which is approximately 4.2 AU. And we want to have that distance in terms of meters. So what is 4.2 AU in meters? 4.2 AU times, we want to get rid of the AU and get our measurement in terms of meters. So it's 1.5 times 10 to the 11. And we get a distance of, let's see here, 6.3 times 10 to the 11 meters. Okay? So that's how far away it is. And the reason I want meters is because second, I want to use the distance equals rate times time relation. This is what should come to mind when you're doing this. And we're asking how long, which means time. So time is equal to what? Well, time will be the distance divided by the rate, which in this case would be 6.3 times 10 to the 11th meters, divided by the rate, which is the speed of light, how fast light travels in the vacuum, 3 times 10 to the 8 meters every second. And when we do this measurement, we do this divided by this, 6.3 divided by 3, then times 10 to the 11 divided by times 10 to the 8. So we subtract 3 from our exponents, and we get the value of 2100 seconds. Okay, that's how long it would take to receive that radio signal. Radio being a form of light, just like infrared or microwave or optical light that we see, the human eye can see. Now, if we divide this by 60, we could get the number of minutes, which is approximately 35 minutes. Okay, and important ideas. So, this gives you an idea of the size, the scale, the vastness of the cosmos, the measurements we need to represent these distances, and how distance is related to time and light. So we use the speed of light a lot here as far as astronomy goes, and it's important to make that connection between this is what we currently are seeing. We're seeing the history of light because this light has to travel vast distances across the cosmos to reach us. So hopefully this gives you some more familiarity with the numbers, some of the astronomical distance numbers that comes into play. And later we'll do some more on angular measures and parallax. Thank you.